So this video I'm going to talk about conditional probability, and that is the idea that the probability of A happening, given that B has already happened, can be given by the probability that both A and B will happen together, divided by the probability that B will happen. This kind of makes sense physically, right? The probability that A has happened, given that B has already happened. Well, B has to have already happened, right? So this probability has already had to have been realized. And then it's the probability that this will happen inside of there. So let's consider my favorite anomalous example of this. So let's consider a very rare disease that affects 1 out of 1,000 people. And we're going to have a test for it that is 95% accurate. Okay? So we're going to look at 100,000 people. Out of 100,000 people, if 1 of 1,000 of them has the disease, then 100 people have the disease, and 99,900 of them do not. If the test is 95% accurate, we would expect out of those 100,000 people that 100 of them, 100 of the diseased ones, 95 of them would test positive, so that is a true positive. But 5 of those people would test negative, right? So it's a false negative for the disease. We would expect that out of the 99,900 that are healthy, that do not have the disease, 94,905 of them, or 95% of them, would test negative for the disease, and 5% of that, or 4,995 people, would test positive, right? That's a false positive. All right, so what's the probability that we will test positive for this disease, right? So it's all of the positive tests, which come out to be 5,090 positive tests out of our 100,000 people, which comes out to be 0.0509 of the probability of testing positive. Okay? And one thing you can notice here is that this is slightly more than 5%, right? We would expect it to be 5% from the healthy people, right? We would expect 5% of these people to test positive. We would expect 95% of these people to also to test positive. So the total probability of being positive we would expect to be a little higher than the 5%, which is the majority of our population. Okay, so what is the probability that we are healthy and test positive? Well, how many of that is there, right? There are the 4,995 of the people. We started out with 100,000 people. So that comes out to be a probability of 0.049. Let's go out to 99. Okay. So we can ask what really good question, right? What is the probability that we are actually healthy, G-A-L-T-H-Y, given that we've tested positive? Okay? So there's a couple ways we can do this. One is we can just look at the positives and then get the probabilities out of that. Or we can use the rule that we got the last time. The probability that we're healthy and positive is this 0.04995, and I'm going to go all the way out there, over the probability that we test positive. The probability that we test positive was 0.0 0.509. So what's the probability that we are actually healthy but had a false positive? Given that we've already tested positive, it comes out to be 0.9813. So 98% of the time, if you test positive for the disease, you do not actually have the disease. And that's because the disease is relatively rare, and the test, even at 95%, that's not great accuracy. That's being wrong 1 out of every 20 times. We look, we see there's a lot more false positives than actual positives, right? About 98 to 1, right? Or, 1 in every 50 diagnoses of this disease is going to be wrong in this case. So that's my favorite anomalous result. Even if you test positive for the disease, yes, you want to have a secondary test to confirm, particularly if the disease is extremely